Hello everyone. In this video, we will learn to explain the postulates that govern VSEPR theory, apply the AXE system to classify three-dimensional molecular shapes, define the bond angle, and explain the factors that affect bond angle, recognize and recall the three-dimensional molecular shapes, explaining the occupation of axial and equatorial positions where relevant. 5. Translate a molecular formula into its three-dimensional molecular shape. One of the major drawbacks of Lewis dot structures is that it does not explain the shapes or geometries of the molecules. The three-dimensional geometry of a molecule has a significant effect on its properties. Therefore, it is very important for us to understand and to be able to predict the three-dimensional geometry of a molecule. The valence shell electron pair repulsion theory, in short, VSEPR theory, does precisely that. The VSEPR theory enables us to predict the shape or geometry of a molecule from its Lewis dot structure. According to VSEPR theory, the shape of a molecule depends on the number of valence shell electron pairs around an atom. That is, all the electron pairs that we represent in the Lewis dot structures. Since the electron pairs are negatively charged, they repel each other. The VSEPR theory states that a given atom in a molecule achieves a geometry in which the electron pairs are located as far apart as possible from one another. This reduces the repulsions between the electron pairs, thus decreasing the potential energy of the molecule and increasing its stability. When we count the number of valence shell electron pairs around an atom in the Lewis dot structure, a single bond, a double bond, a triple bond, a lone pair, or a single electron, all of them are treated as one valence electron pair. For example, in the Lewis dot structure of hydrogen cyanide, the carbon atom forms one single bond with hydrogen and a triple bond with nitrogen. Each of these bonds are counted as one valence shell electron pair. Even though the triple bond consists of 3 electron pairs, it is still counted as one valence shell electron pair. Therefore, the total number of electron pairs around the carbon atom in hydrogen cyanide molecule is 2. Similarly, for ammonia, the central atom nitrogen has 3 single bonds with 3 different hydrogen atoms and one lone pair around it. Single bonds are counted as one valence shell electron pairs, and each lone pair is counted as one valence shell electron pair. Therefore, nitrogen in total has 4 valence shell electron pairs around it. In this video, we are going to use the following notation to represent various molecules and geometries. The molecule is represented by writing A, X, subscript M, E, subscript N, where A is the central atom and X is the terminal atom, where subscript M represents the number of terminal atoms, and capital E is the non-bonding electron pair, and the subscript N represents the number of non-bonding electron pairs. Let us start with the simplest type of molecule, AX2. That is, the central atom has two terminal atoms with 0 lone pairs on it. Since all types of bonds, that is single, double and triple bond, are treated as one valence shell electron pair, no matter how the terminal atoms are connected to the central atom, they are always counted as one valence shell electron pair. Therefore, the total number of valence shell electron pairs is equal to the total number of atoms on the central atom plus the lone pairs. Since AX2 does not have a lone pair, the total number of valence shell electron pairs is equal to number of atoms, that is 2. An example of such molecule is beryllium chloride, BeCl2. These two electron pairs push each other as far apart as possible in the three-dimensional space, giving the molecule a linear shape with a bond angle of 180 degrees, where the bond angle is the angle formed by the nuclei of two terminal atoms with the nucleus of the central atom. Few other examples of the molecules of type AX2 are carbon dioxide and hydrogen cyanide. Note that the multiple bonds, that is a double bond and triple bonds, are treated as one valence shell electron pair. The next type of molecule is of AX3, that is, the central atom has 3 terminal atoms with 0 lone pairs on it. So the total number of valence shell electron pairs on the central atom are 3, and all of them are bonding pairs. An example of such molecule is BF3. These electron pairs push each other as far apart as possible in the three-dimensional space, giving the molecule a trigonal planar geometry. The bond angle is 120 degrees. Let us try to visualize this geometry. Draw an equilateral triangle on a piece of paper and cut it out. The center of the triangle is where the central atom sits, that is boron. And the 3 corners of the equilateral triangle has terminal atoms, that is the fluorine atoms. Note that all the atoms in the molecules are on the same plane, that is, this molecule is planar. Few more examples of the molecules of type AX3 are BF3, SO3, NO3-, etc. The next type of molecule is AX2E. That is, the central atom has 3 valence shell electron pairs around it. 2 of them are bond pairs and 1 of them is a lone pair. An example is sulfur dioxide. There are 3 valence shell electron pairs around the central atom, which means the geometry of electron pairs, also known as electron geometry, is still trigonal planar. However, if we define the shape of the molecule, one of the corners of the equilateral triangle does not have an atom there. Therefore, the remaining shape looks like a bent shape or V-shaped molecule. Therefore, for the sulfur dioxide molecule, the electron geometry is trigonal planar and the molecular shape or geometry is angular or bent or V-shaped. There are some important differences between how a lone pair and a bond pair affects the geometry of a molecule. The lone pairs are localized on the central atom, while the bonding pairs are shared between the central atom and the terminal atom. Therefore, the lone pairs on the central atom occupy more space compared to the bonding electron pairs. Consequently, the repulsion between two lone pairs is greater than a lone pair and a bond pair, which is greater than the repulsion between two bond pairs. These uneven repulsions affect the molecular geometry and result in deviations from the ideal bond angles. For example, in sulfur dioxide molecule, the repulsion between the lone pair and bond pair are greater than the repulsion between a bond pair and another bond pair. Therefore, the bond angle of oxygen, sulfur and oxygen is less than the ideal bond angle of 120 degrees. Similarly, a double or a triple bond have greater electron density than a single bond. Therefore, they repel single bonds more than two single bonds repel each other. For example, in formaldehyde molecule, the bond angle between two hydrogens which are connected to carbon atoms by a single bond is lower than the ideal bond angle of 120 degrees, and the bond angle between an oxygen atom and a hydrogen atom is greater than the ideal bond angle of 120 degrees. The next type of molecule is AX4. That is, the central atom has 4 terminal atoms with 0 lone pairs on it. So the total number of valence shell electron pairs on the central atom are 4, and all of them are bonding pairs. An example of such molecule is CH4, methane. These electron pairs push each other as far apart as possible in the three-dimensional space, giving the molecule a tetrahedral geometry. The bond angle for a tetrahedral geometry is 109.5 degrees. Tetrahedral geometry is a non-planar geometry. That is, all the atoms in the molecule are not in a single plane. Therefore, we can say that the tetrahedral geometry is a non-planar geometry. To represent the three-dimensional geometries that are non-planar, we use different kinds of bonds. The bond represented by a solid line means that it is on the plane of paper. The dashed line represents a bond that is going into the plane of the paper and away from you. The bond represented by a wedge is coming towards you. Few more examples of molecules of type AX4 include SiCl4, sulfate ion, which is SO42-, and ClO4- ion. The next type of molecule is of AX3E. That is, the central atom has 4 valence shell electron pairs around it. 3 of them are bond pairs and 1 of them is a lone pair. An example of such molecule is ammonia, NH3. In ammonia, nitrogen has 3 single bonds around it and 1 lone pair. So, overall, there are 4 valence shell electron pairs, which means the geometry of electron pairs which is also known as electron geometry, is still tetrahedral. However, one of the corners of the tetrahedron shape does not have an atom, and it is replaced by a non-bonding electron pair, also called as lone pair. Therefore, the remaining shape looks like a trigonal pyramidal with a bond angle of less than 109.5 degrees. Note that the trigonal planar structure is different than that of trigonal pyramidal structure. The trigonal planar, as the name suggests, is a planar structure, that is, all the atoms of the molecule are in one plane. However, trigonal pyramidal structure is not a planar structure. The next molecule is of type AX2E2, that is, the central atom has 4 valence shell electron pairs around it. 2 of them are bond pairs and 2 of them are lone pairs. An example of such molecule is water, in which there are 2 single bonds around oxygen and 2 lone pairs on it. There are overall 4 valence shell electron pairs around the central atom, which means the geometry of electron pairs is still tetrahedral. However, 2 of the corners of the tetrahedron shape does not have atoms. Instead, we have lone pairs or non-bonding electron pairs. Therefore, the remaining shape looks like a bent shape, also called as V shape. The bond angle of this shape is 104 degrees, which is less than 109.5 degrees, the ideal bond angle of a tetrahedron shape. The next type of molecule is AX5, that is, the central atom has 5 terminal atoms and 0 lone pairs on it. So, the total number of valence shell electron pairs on the central atom are 5, and all of them are bonding pairs. An example of such molecule is PCl5. As we can see from the Lewis dot structure, it has 5 single bonds around phosphorus and 0 lone pairs. That is, the total number of valence shell electron pairs are 5. These 5 electron pairs push each other as far apart as possible in the three-dimensional space, giving the molecule a trigonal bipyramidal geometry. There are 2 different bond angles for this geometry, which is 90 degrees and 120 degrees. Let us now try to visualize this structure. Take a piece of paper and cut it into an equilateral triangle. Take a pen or pencil and pierce the paper exactly at the center of the equilateral triangle and push the pen halfway through. The pen has to be perpendicular to the plane of the paper. Now, imagine that the center of the equilateral triangle is the central atom, in this case phosphorus. Each of the 3 chlorine atoms are pointing towards 3 corners of an equilateral triangle, and the remaining 2 chlorine atoms point towards both the ends of the pencil that is perpendicular to the equilateral triangle. Few more examples of the molecule of type AX5 are SOCl4 and ASF5. The AX5 type molecule has 2 different spatial positions, axial and equatorial position. The equatorial positions are on the plane of the triangle, while the axial positions are above and below the plane of the triangle. The angle between 2 equatorial positions is 120 degrees, and the bond angle between an axial position and an equatorial position is 90 degrees. Therefore, the repulsion between two equatorial positions is weaker than that of the repulsion between an axial position and an equatorial position. When one of the bond pair in this geometry is replaced with a lone pair, the lone pair is placed in the equatorial position to minimize the repulsion. Let us now look at those examples. If one of the bond pairs is replaced with a lone pair, we get AX4E type molecules. As discussed earlier, the lone pair occupies an equilateral position. The electron geometry is still trigonal bipyramidal. However, one of the corners of the trigonal bipyramidal shape does not have an atom. Instead, it is replaced with a non-bonding electron pair. Therefore, the remaining shape looks like a seesaw shape. That is, the molecular geometry for AX4E is seesaw shape. Examples of such molecules include SF4, IF4+, XeO2F2, etc. Now, if two of the bond pairs are replaced with lone pairs, we get AX3E2 type. Both of the lone pairs occupy equilateral positions. The electron geometry is still trigonal bipyramidal. However, two of the corners of the trigonal bipyramidal shape does not have an atom. Instead, we have a non-bonding electron pair. Therefore, the remaining shape looks like a T-shaped molecule. That is, for AX3E2 type, the electron geometry is trigonal bipyramidal, but the molecular shape is T-shape. Examples of such molecule include ClF3, BrF3, etc. Next, if three of the bond pairs are replaced with lone pairs, that is, of type AX2E3, all the three lone pairs occupy equilateral positions. The electron geometry is still trigonal bipyramidal. However, three of the corners of trigonal bipyramidal shape does not have atoms. Instead, we have lone pairs. Therefore, the remaining shape looks like a linear shape. The next type of molecule is AX6. That is, the central atom has 6 terminal atoms with 0 lone pairs on it. So, the total number of valence shell electron pairs on the central atom are 6, and all of them are bonding pairs. An example of such molecule is SF6. Sulfur has 6 single bonds around it and 0 lone pairs. Therefore, the total number of electron pairs are 6. These 6 electron pairs push each other as far apart as possible in the three-dimensional space, giving the molecule an octahedral geometry with a bond angle of 90 degrees. Let us try to visualize this structure. Take a piece of paper and cut it in the form of a square. Then we take a pen or pencil and pierce the paper exactly at the center of the square and push the pen halfway through. The pen has to be perpendicular to the plane of the paper. Now imagine that the center of the square is the central atom, that is sulfur, and 4 of the fluorine atoms are pointing towards 4 corners of the square, and the remaining 2 fluorine atoms point towards both the ends of pencil, one above the square and one below the square. If one of the bond pairs is replaced with a lone pair, we get AX5E type. The electron geometry is still octahedral. However, one of the corners of the octahedron shape does not have an atom. Instead, we have a lone pair. Therefore, the remaining shape looks like a square pyramidal. Some of the examples with square pyramidal shape are BRF5, XEOF4, etc. If two of the bond pairs are replaced with lone pairs, we get AX4E2 type. The electron geometry is still octahedral. However, two of the corners of the octahedral shape does not have atoms. Instead, we have lone pairs. Therefore, the remaining shape looks like a square planar shape. Examples: XEF4 and ICL4-. One of the most common types of questions that we ask in the exam is, we give you a molecular formula and ask you to determine the molecular shape and the bond angle of that molecular formula. Now, here are the steps that we need to follow to be able to convert molecular formula into a molecular shape. First, we draw the Lewis dot structure of the molecule. We have practiced this step extensively in previous videos. Step 2. Count all the electron groups, both the bonded and non-bonded, around the central atom. Third step. Use the following table to find the molecular and electron geometry around the central atom.